coefficients that are basically changed. We don't change any of the subscripts in the formulas or anything like that. We just really, the numbers that come in front of the formulas. The ultimate goal is to end up with the same number of atoms of each element on each side. We obviously could do that. A good way, again, as we did last time, was, kind of make a table and kind of add up what's on each side, and obviously keep putting coefficients until you get to the same ones. Sometimes if we were using just polyatomic ions, or there's polyatomic ions on both sides of the equation that look the same, sometimes it's a lot easier, as we talked about, to sort of keep those guys together and just balance them as sort of polyatomic ions as like units on each side. And a lot of times it will come together fairly well and easy for you than going sort of element by element in those cases. There's really kind of two major things that you want to make sure of when you balance an equation. And one is you want to make sure that when you are all done, clearly you have the same number of elements on each side. The other thing that you want to make sure of is that all of the coefficients are whole numbers. So we saw that we can use a fraction to balance, but you do need to make sure that it ends up being a whole number. Otherwise, it's not properly balanced and would be considered wrong. And the other thing is you need to make sure that it is the simplest set of whole numbers that are balanced in that sense. And what that means is, again, if you look across all of your sort of numbers on the coefficients, you can reduce everybody by a common number and still end up with that whole number. When it's all said and done, you should go through and divide everybody by that common number. So all whole numbers when it's all said and done, the simplest set of whole numbers, and same number of elements on each side is basically your balancing here. Any questions on that there? Okay, those coming in, again, I apologize. It's not been a banner week for me and the links. So my mistake totally, and I do apologize for that. So let us continue on here and talk about different types of reactions and ways to classify reactions. First off, how do we know sort of a reaction is taking place, or, what are some driving forces for reactions? And when we talk about reactions, there's kind of three driving forces for reactions. And one is a solid being formed, which is what's sometimes referred to as a precipitation reaction. Water being formed, which is obviously the formation of H2O, and also a transfer of electrons. So those are three really driving forces for reactions. And what that really means is those are the three things that really are what reactions do, in a sense. That is really what they make. They either sometimes make a solid, they sometimes make water. Are there some electrons that are being transferred between one and another? And that's ultimately what is transpiring when we look at sort of chemical reactions. Now, there's different ways you could classify chemical reactions, and I'm going to skip the part about redox reactions for the time being. We'll come back to them in a later chapter. So in your notes, this is a little bit ahead of in the notes that you have. So pick up on your notes where it says synthesis and combination. So the first type of reaction is a synthesis or combination reaction. And that is a reaction where it has a general form of A plus B makes AB. Essentially, we're going to take two things and make one thing here. And that's your classic synthesis or combination. So basically putting things together, hence the name combination or synthesis. And that's what we see here, formation of water. Two things make one thing, classic looking combination reaction. Two things here when we make sodium chloride, make one thing here. Again, your classic sort of synthesis or combination reaction, basically putting those things together. Another way that we could classify a reaction is actually the opposite of this reaction, and that is a decomposition reaction. In a decomposition reaction, unlike a synthesis reaction, we're kind of going the backwards route here. We're starting with one thing and we're making a couple things or maybe three things. So here, if we ran an electrical current across water, starting with one thing, making multiple things on the product side, that is your classic decomposition reaction of what it looks like. This is mercury 2 oxide When we sort of heat that up, we get mercury and we get oxygen gas. Again, one thing making multiple things is a decomposition. So a good way to remember that is synthesis, you kind of put it together, and decomposition, you basically break it apart. So one puts it together, one kind of breaks a reaction apart. And those are two very common ways that we classify chemical reactions. Another classification is one which is known as a single replacement reaction. And in a single replacement reaction, much like the title sort of implies, we have somebody coming in to the reaction and replacing it. So for example, here, if A was a metal, this would be a metal all by itself, uncombined, no charge. This is an ionic compound that has a positive and negative. And what happens is this metal will come in and kick out the positive guy. When it kicks out the positive guy in that ionic compound, it actually comes out all by itself with no charge. And then it makes a new ionic compound on the other side. A could also be a nonmetal, and a nonmetal plus a positive and negative guy will do a similar reaction, except that the nonmetal, although it does not have a charge here, when it gets a charge, it's negative. So it will come in and kick out the negative guy there, making that nonmetal now come out all by itself, no charge, and a new ionic compound happening. So that is a classic single replacement reaction. The element coming in order for that reaction to take place, it needs to be more reactive than what it's replacing. So in the case here, we look at zinc. This is zinc all by itself, which means zinc has no charge here. This is hydrochloric acid, which is a positive guy and a negative guy. Zinc is a metal, which means when it does gain a charge, it doesn't have one yet, but when it does gain a charge, it will actually go in and kick out the hydrogen. When it does, hydrogen comes out in a sort of elemental form all by itself, and it comes out as H2. And if you did this, that would be generating a gas, which would be bubbles that you would actually see actually happening in the test tube. Then the zinc, as it comes in, that is when the zinc will actually gain a charge of +2, and our chloride will have a -1 charge and makes a new ionic compound. This reaction will actually take place, and what that means is zinc is actually more reactive than hydrogen because this reaction took place. Now, if you swapped out, say, copper, for example, this reaction actually will not take place. You'll get no reaction. And what that means is copper is less reactive than hydrogen. You could also do this with, say, nonmetals. So very common ones are halogens. So if you had something like Br2 plus some sodium iodide, Br2 is how it naturally comes. Group 7, they're diatomic. There's no charge associated with it. Sodium is positive, iodine is negative. In this case, bromine would normally have a negative charge, which means it actually goes and takes out the negative guy here. It's at that point that bromine gains its normal charge of Br minus, and that hooks up with sodium, which is an Na plus, and that's how we get to NaBr in this particular case. When the iodine comes out, it comes out in its natural form, which is diatomic, also has no charge here. Also should balance this like we talked about the other day, put a couple of 2s there, and now we're balanced. So this again is a single replacement reaction. What this would tell us is bromine is more reactive than iodine in this case because this reaction would take place. Any questions on a single replacement reaction? Yeah.
Can you, I'm getting kind of confused. Do you think, I don't know, this seems like a lot of, can you explain it like a little slower one more time?
For the single replacement reaction?
Yeah.
Yeah. So in a single replacement reaction, basically the element or that's by itself, the atom that's by itself. So like in the case of zinc is all by itself, which means it's just a solid piece of zinc metal that you would take. And basically, if you did this, you would have the hydrochloric acid in here. You would take a piece of zinc metal, and basically you would drop it into the hydrochloric acid. When it does that, it's going to follow this single replacement reaction. And basically the idea here is zinc does not have a charge to begin with, but this hydrochloric acid is sort of an ionic compound in the sense, and it has a positive guy and a negative guy. So because this is a metal, and although it does not have a charge at this part, yeah, single displacement, single replacement. Sometimes people call it a single exchange, all the same. So single displacement, single replacement, exactly the same. The zinc here does not have a charge, but because it's a metal, what we know about metals is when they do gain a charge, it is going to become a positive charge. And because it's going to become a positive charge, it needs to come in and actually kick out the positive guy. Why does it need to kick out the positive guy? If it didn't kick out the positive guy and it kicked out the chloride, what we would be left with is H plus and Zn2 plus. These two guys are positively charged, which means they're definitely not going to come together because things with the same charge won't basically bind to each other, right? So when the zinc comes in, it kicks out the hydrogen. And what ends up happening is the hydrogen actually ends up all by itself in this sort of natural, uncombined situation. And what it's at that point that that's occurring, that's actually when the zinc will then gain its normal charge of +2. And that's will allow it to come together with chloride that has a -1 charge from here. And then these two guys will come together and make a new ionic compound, which is ZnCl2 in that particular case. And this again is a single replacement reaction because one guy is coming in and replacing another. So it's like a one-to-one sort of replacement that's happening in this particular reaction. And again, it's a metal, so it will replace the positive guy. And if it's a non-metal, like in the example over here, it normally, because this is a non-metal, it normally will be a negative charge, although it doesn't have a charge here. And that's why when it comes in, it needs to replace the negative guy. So these things coming in will actually replace it. And what's really happening along the way is this. We basically have zinc and we have H plus and Cl minus that's kind of floating around in the solution. And when the zinc goes for a swim and it starts to react, what's going to happen is actually the zinc's going to lose electrons. And that zinc, when it loses electrons, when it goes for a swim in the solution, becomes positively charged, which is why it's floating around in the solution, along with the chloride ion. Those electrons that are lost by the zinc are actually going to be grabbed up by the hydrogen. And when H plus gains those electrons, H plus becomes hydrogen gas. And that's what you will start to see sort of bubbling out of the solution as the zinc is doing that. This is what is sometimes referred to as a redox reaction. Basically, the zinc is losing electrons. The hydrogen or H plus is gaining the electrons. And when it gains electrons, the hydrogen ends up getting what is referred to as being reduced to H2, which is really the molecular form of hydrogen. And that's the gas that you see sort of bubble up through there. And that's why we say the zinc and the chloride come together, because if you look what's really left in the solution at that point, it's just these two guys that are there to come together. The hydrogen again has become, the H plus has become H2 and basically has bubbled out of the test tube, if you will. So it's only the zinc and the chloride that are there to basically come together, and that makes zinc chloride. It's actually aqueous, which means you won't see anything. It'll just look like solution. But what's really floating around that solution is zinc ions and chloride ions. Now, in order for whatever is coming in, like for example here, the zinc, in order for that guy to come in, he has to be more reactive than what it's replacing. So if you did this, We'll talk about aqueous in the next chapter when we talk about solutions. But anything that has a charge that's in a solution is aqueous, basically. So any ions that are floating around, anything that says AQ that's aqueous, basically means it's really not together. What that really means is when you have a solution, you have these ions basically floating around kind of free in the solution part. And to you, it'll just look probably colorless solution because zinc is colorless, chloride's colorless. So it will just kind of look like the water part of the solution, but really in that water part of the solution or the colors part of the solution is the zinc ions floating around, the chloride ions floating around, and stuff like that. But in order for this reaction to take place, and if you did see this reaction take place, what that means is, in this case, the zinc is actually more reactive than hydrogen. If it wasn't more reactive, you would actually see nothing occur, which was the example up here. If we swapped out zinc for copper and put it in there, you would absolutely positively see nothing occur because copper is actually less reactive than hydrogen. You don't have to worry too much about which one's more reactive or less reactive in terms of predicting if a reaction will occur or not. But if you were physically doing an experiment like this and you saw the bubbles start to occur when you put the zinc in the hydrochloric acid, you know this reaction took place, and that would automatically tell you that the zinc is more reactive than hydrogen. If you drop the copper into hydrochloric acid and didn't see anything occur, really no bubbles, kind of looks the same, you would know that copper and hydrochloric acid did not react with each other. And the reason they did not react with each other is because copper is less reactive than hydrogen. Questions on that? So really what's sort of happening here is single replacement reaction is really what is referred to as a redox reaction, which we kind of skipped. We'll come back to it though. But it's really a transfer of electrons that are happening here. And that's one of those driving forces for a chemical reaction. And it's really that transfer of electrons from the zinc to the H plus in this particular example that's going to drive that reaction to actually take place. What you would actually see if you watched this or did this reaction is this piece of zinc that you would toss in there, it would eventually kind of dissolve and go away. You wouldn't see anymore. And that's because what's happening is on the zinc, if you want to think about it, every time zinc loses electrons, the solid zinc basically jumps off of the solid into the solution part and becomes zinc with a +2. So it starts floating around basically. At some point, all the zinc molecules will probably jump off. And that's why you slowly start to see the piece of zinc kind of dissolve, 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 and then it's eventually gone. This is accompanied by all those electrons that are coming off, hitting the H plus and making that hydrogen gas and all those bubbles that you would see in the test tube as this is happening. Question on that?
Quick question, Professor.
Yeah.
If we were to see this question on a test,
Yeah.
like would how could we expect it? Like, would we have to like fill out the products and then balance it, or is it just like
To be truthfully honest with you, probably you probably wouldn't have to do that for a lecture part. You know, you might have to do that maybe in the lab or something, but for lecture part, you wouldn't have to do that. It would probably be a question like you were given, for example, the reaction I scribbled on up there on top, the zinc and the hydrochloric acid, and you know it went to the H2. So you're given that actual equation. It might be a question like classify this reaction as like a synthesis reaction, a decomposition reaction, a single replacement reaction, you know, a double displacement reaction. So it'd probably be more like the equation would probably be given to you. You might have to balance it maybe, but then it would probably just ask you simply looking at it, you know, what type of classification would you give to it rather than
okay?
predicting products? Yeah.
Would we also have to classify the state of matter? That
Probably not at this point. I technically that's in the solutions chapter. I think when we talk about solubility and stuff like that. So you wouldn't have to do that particularly for us. It would be okay because we technically haven't talked about how to necessarily figure out, you know, what things are solid or aqueous and that type of stuff technically yet. So at this point, you wouldn't have to worry too much about the states of it, of the matter of each of those guys.
Okay, thank you.
You're welcome. Other questions? Okay, so that's a single replacement reaction. And again, a lot of these will really sort of match up to these sort of general formulas of them. So again, if you look at this, we have A, which is just something by itself. That's like zinc. That's what it looks like. We have an ionic compound, and this is a positive and negative guy. So right off the bat, that looks very much different than, like the one that we looked at previously here, where, we have one thing that's starting, and then we made two things or more things. So this type of reaction, decomposition, looks very different than a single replacement. And then obviously that looks very different than the synthesis reaction, where we have, two things make one thing, and you can almost do that. Two things make one thing. That's definitely a combination. Two things make one thing. It's definitely a combination reaction. So these sort of general ways that these reactions look like are things that you want to remember. And if you're given an equation, you literally, no two sort of classification of reactions in that sense will kind of look the same or kind of be set up the same. Here we got 2 makes 1. Again, 1 makes 2. Here we have something with no charge and an ionic compound. So these are all things that you want to look at if you're sort of analyzing an equation. The general, like, okay, I got this and this that makes this. That looks just like how a single replacement reaction looks, or something of that nature. So those general sort of like A plus B and stuff like that, that you want to kind of look at those things to help you sort of identify what's going on. And these 3 reactions that we just talked about are definitely going to be different than this type of reaction here. And this is what is known as a precipitation reaction. And it's a precipitation reaction because it makes a solid in this particular case. So a precipitation reaction is really a type of reaction which is known as a double displacement reaction. And really a double displacement reaction is like the big umbrella under which all these things, or this type of reaction, is sort of classified. Zinc does have a +2 charge, but not on the left-hand side when it's by itself. So if that's your question, anything that is sort of by itself from the periodic table has no charge. Things only get charges when they hook up with, for example, a metal and non-metal, if that's sort of your question.
Yes, thank you.
So on the double displacement, it has a general formula of A, B plus C, D. And just looking at this general arrangement, this is much different than our synthesis. This is much different than our decomposition. This is much different than our single replacement. What's important about this is these are 2 ionic compounds. So a positive negative guy, a positive and negative guy that's happening there. So that sort of setup, when you look on the left-hand side of the arrow, just like we see here, this is a positive negative guy. That's potassium ion and chromate. That's barium ion and nitrate, a positive negative guy. So that is the general sort of setup for a double displacement reaction, which is the same thing as a precipitation reaction. Again, a precipitation reaction is just called that because it forms an actual solid there. But what happens in a double displacement reaction is essentially the 2 positive guys, they basically switch partners. So A, which is positive, will then go hook up with D on the other side and make a new ionic compound. C, which is positive, will hook up with the B that's negative and make a second new ionic compound in this case. And if we look at our sort of example on the bottom, this guy is that situation. This is our positive guy in the first. He's going to then hook up with the negative guy in the second one. And if we look over here, that is how we get to the potassium nitrate. Those 2 guys basically got together there. Now, this chromate is the negative guy in the first one. He will then hook up with the positive guy in the second one. And that is how we get to our barium chromate. This is why it's called a double displacement. Unlike the single, we actually have 2 ions swapping places. And that's why, again, double displacement reaction. Again, a precipitation reaction is a type of double displacement reaction. So kind of under the big umbrella of a certain type of reactions is double displacement. And one type of double displacement reaction is one that's referred to as a precipitation reaction because it actually makes a precipitate. Any questions on that? Now, here's another example of that, which is actually the same example. But again, what's happening here is that double displacement, the switching of those ions. Again, the potassium goes and hooks up with the nitrate. The barium then goes and gets the chromate. And again, referred to as a precipitation reaction because a solid happened to be formed. Another type of double displacement reaction, which actually does not make a precipitate, is actually an acid-base reaction. So an acid-base reaction is another type of double displacement reaction, but it actually will end up making water. So if you remember those three driving forces for reactions, that was an electron transfer, which we saw in our single replacement reactions, right? The zinc losing electrons, the H plus gaining electrons. The second one was a precipitate that it was made, which is what we saw in our precipitation reactions. The third driving force is actually the formation of water. So making water, which is what we see here with our acid-base reactions. So these are, really the things that are sort of happening here. An acid-base reaction, this is an acid, that's acetic acid, not acetic acid, that's hydrochloric acid. This is a base, which is potassium hydroxide. And whenever you take a strong acid and strong base, you basically will always make two things. You will make water, and you will make what is referred to as a salt. And a salt is a fancy word for an ionic compound. This basically means we have a positive and negative guy together. But what is really happening here is the exact same thing that we talked about earlier. That's not what I want. Come here. There you go. This is a positive and negative guy. This is a positive and negative guy. So as soon as you see those two positive and negative guys, that should automatically make you think double displacement reaction. Because what's going to happen is our two positive guys are going to switch partners. So what ends up happening in this case is the hydrogen, which is positive in the first guy, will then go with the hydroxide, which is negative in the second guy. And when H plus and OH minus come together, that is always, in the case of an acid-base reaction, where our water comes from. H plus OH minus is basically where we produce water from. What that leaves you is the K plus, which is the positive guy and the second guy, will then go and hook up with the Cl minus there in the first guy and make our second ionic compound, which is potassium chloride and the salt. So although this is oftentimes referred to as an acid-base reaction, and oftentimes it's referred to as a acid-base neutralization reaction, because the ultimate thing that's happening in this reaction, we're making water basically, is actually what's happening. That's actually the thing that's being made and is happening in this reaction. And that's why it's sometimes referred to as a acid-base neutralization reaction. So this type of reaction could be classified as acid-base neutralization reaction. It is under the big umbrella of double displacement reactions, along with precipitation reactions, which are also under that umbrella of double displacement reactions. So if you kind of think about, there's actually two major sort of umbrellas of reactions. One are known as redox reactions, which stand for oxidation and reduction reactions. And what that really means is oxidation is when somebody loses electrons. Reduction is when somebody gains electrons. And sort of underneath that sort of big umbrella, we have things like synthesis reactions. We have things like decomposition reactions. And we have things like single replacement reactions. The other really big umbrella is our double displacement reactions. And underneath this sort of big umbrella are the two kind of reactions we just saw. A precipitation reaction, which is still a double displacement reaction. It just means that we formed a solid made. And an acid-base reaction, which usually will mean that we made water. So these are sort of the big umbrellas of classifications. These are kind of like sub-classifications of reactions. And as you could probably see here, you could actually classify the same reaction in multiple ways. It just kind of depends on what you're sort of looking at in terms of that. Any questions on that type of classifications there? We do have one more classification that we could add to sort of the list, and this is a combustion reaction. And a combustion reaction, you know, most of the time will involve oxygen, produce heat in a flame, especially when you're doing an organic combustion reaction. So an organic combustion reaction, which is what these guys are, and down here, is we have some type of organic guy, which basically has carbon, hydrogens, maybe oxygens involved, some organic. And the classic things of a combustion reaction or an organic combustion reaction is the presence of O2 on the left, and it will always make CO2 and water on the right-hand side. So if you're dealing with a combustion reaction, O2 on the left, products, if you had to figure out what the products are, especially if you're starting with some type of organic guy, always going to be CO2 and water is always the things that are going to be made. Now, there's a more generic definition of a combustion reaction, and that is simply a reaction, kind of this part of it, that involves oxygen. So really, a reaction that involves oxygen could technically be classified as a combustion reaction. So you could have technically something like this, magnesium plus some O2 makes some MgO. And technically here, it has oxygen. So this technically would be a combustion reaction because of that. But if you even look at this reaction here, based on our conversation, you might even classify this as this is one thing, two things make one thing. So two makes one. You could also obviously classify this as a synthesis or combination reaction as well, right? Because of that. So you can definitely classify the same reaction in multiple ways, depending on sort of what you're looking at. Any questions on how to classify reactions there?
I actually just have. Oh, sorry.
Yeah. Do you want to chat me it? Yeah. Yeah, so there could technically be probably in a question, for example, you know, a question maybe that you would come across maybe in the lab or you know, in an exam or something like that. There probably will be one best answer, if you will. But technically speaking, you could classify multiple reactions, you know, in at least a number of them in at least two different ways. So, for example, if you looked at you know, that reaction that we saw previously here. When we go back over there, where did it go? You know, for example, this reaction here, you could absolutely classify this one as a double displacement reaction because it technically is a double displacement reaction that's happening. But you could also classify it as acid-base neutralization reaction. And out of those two choices, for example, here, most people would probably pick the acid-base sort of classification because that's really what, you know, HCl and KOH is. It's an acid and base. But it technically wouldn't be wrong to classify it as a double displacement reaction because that's essentially what's happening. And same thing here if we look at the one previous to that as well. This particular one could also be classified as a double displacement reaction, but a lot of times people will classify this as a precipitation reaction because of the solid that's being formed. So those are both good classifications. My guess, though, if you came across a problem, it would probably give you either one of those options. So you probably either have the double displacement as one of the options, or you might have the precipitation as one of the options. Probably in a real type question, you might not have both sort of given to you if that's sort of your question there. And that's okay. Was that Patricia that was trying to ask a question? And again, if you do have questions, feel free to type it in unless I just answered it. I don't know if I did. Okay, perfect. Okay. Yeah. Okay, then other questions on classifying reactions? Perfect. So now what we're going to talk about, though, is we're going to talk a little bit about molar mass and Avogadro's number. And where we're going with this is we're sort of talking about balancing reactions, types of reactions. We're going to actually eventually, towards the end of this chapter, talk about how to do calculations from actual chemical reactions and equations. But it does start with molar mass and Avogadro's number. And really, it starts with our good friend, the mole. And that, unfortunately, is not the furry little guy there, but it is a mole.
Professor, I do have a question. I'm sorry. I think I'm gonna have to take you back.
Okay.
Do you think that you would be able to explain a little bit about decomposition reaction?
Yeah, in terms of
like what the results are? Because this was like regarding the lab.
Yeah.
It was just like a little bit hard to understand.
It's hard to sort of tell you exactly in the sense of if your question is kind of like what do you get on the product side always. There's not necessarily a for sure answer for that per se, but I can tell you that a couple of things commonly happen in decomposition reactions. For example, here, before I started scribbling on it, this water obviously had oxygen involved. And usually when you have oxygen, if you're doing some type of decomposition, O2 gas is usually generated as a result of that. Same thing here. You can kind of see this guy has some oxygen in it, and it will also sort of generate some O2. So that's a common sort of product that you will get. It kind of does depend, though, on you know, sort of what you're dealing with, because you could have something like this, which this is carbonic acid, and carbonic acid will, even though it has oxygen involved here, you might be tempted to go, oh, it's going to make O2. But in this particular case, it actually won't make O2. It will actually make something else that's like gas. It will actually make water and carbon dioxide gas. So unfortunately, I can't really give you, like, you know, in a combustion reaction where, you know, you always got that and this is always the products. And that's in like an organic combustion reaction. In a decomposition reaction, it does sort of depend on what you're starting with as to what will sort of be produced along the way. So for example, like potassium perchlorate or something like that, you know, you would make something perhaps like KCl. And again, this guy does have O, you make some oxygen as well. So, you know, it does sort of depend on what you're starting with and stuff like that as to what you would produce. But a lot of times things that do have oxygen on the left will end up kind of, as it's decomposing, produce some oxygen gas. But again, it's not always 100% the case. As you can see here, you know, you do make some CO2. So there's not a real good formula. And for lecture part, you won't have to worry too much about that aspect of it, that you could kind of follow to kind of know what was there. But a lot of times if there's an oxygen involved, that definitely is, a lot of times will end up as like O2 on the product side. Okay. And absolutely, like what it says there, and as we talked about there, they're basically opposites of each other. So decomposition is like breaking something apart, while the combination is kind of putting it together. So it's hard to sort of for sure tell you, like, this is always what you get. One place where you could kind of do that for sure, it's what you get is with that organic combustion. But unfortunately with that one, it's a little trickier sometimes, that particular one. Okay, then let us get into the mole. And the mole is really a term that we use in chemistry to really describe a certain amount of something. So if you remember, in life, there's a lot of words that, mean something. So for example, right, if we say we have a pair of something, that's referring to having really two of something. If we have a dozen of something, that's 12. I guess they still use that occasionally. They used to use it with pencils a lot. If you have a gross, that's 144. For chemistry, we do have a term that refers to something, and that is what is referred to as a mole. And you might not believe this at this point, but that is actually the abbreviation for mole. It's not a big word, so they had to cut something off, so they cut the E off. So when you do see MOL, that is the abbreviation for mole and not molecule. So just keep that in mind. That's a very common thing sometimes people get confused with. That the MOL abbreviation is the abbreviation for a mole. And it's basically the amount of substances that are contained in atoms, molecules, particles, and exactly 12 grams of that carbon-12 isotope. And you might remember that the carbon-12 isotope was the one that they used as the standard to make the atomic mass that we see on the periodic table. That was the isotope that they compared everybody to really figure out that atomic mass number that we see on the periodic table. Here again are just some words. We'll come back to this picture, I think. But what does a mole really represent sort of numerically? And there actually is a value associated with a mole. And 1 mole of anything will equal what is referred to as Avogadro's number. And that number is rounded most of the time to 6.022 times 10 to the 23. Now, the units of it are a little bit different as well. The units could be particles. They could be molecules. They could be atoms, if you're talking about atoms. They could be pizzas, since it's dinner time. Shoes, not because it's dinner time. So they really can be anything you want here in terms of the units, but the number is always the same. What do we use Avogadro's number for? And sometimes people overuse Avogadro's number because they're essentially like, I learned this number, I should definitely use it along the way here. But we use Avogadro's number really to go from moles to atoms or molecules or particles and backwards. And we use it as a conversion factor. We could say that there are 6.022 times 10 to the 23 atoms per mole. Or again, you could flip it around and put the mole up on top and the 6.022 times 10 to the 23 atoms on the bottom. So we use this really as a conversion factor to go between moles. And although I wrote atoms, it technically, in most cases in chemistry, these are the 2 common units that we use with it, either molecules or atoms in that particular case. So you don't want to use it in every situation. You want to use it when you are given something in a problem that mentions something about atoms, mentions something about molecules, or you're asked in a problem to solve for something like atoms or molecules. If you not mention any of those things in a problem, leave Avogadro's number alone. Don't use it. People, again, tend to try to use it in every calculation. But again, you pretty much need something that says moles, something that says Atoms are molecules. And again, if you don't see it, don't use it. The term mole is again represents its Avogadro's number. And you could pretty much from the periodic table, for example, you could say 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. You could say 1 mole of silver would have 6.022 times 10 to the 23 atoms of silver. Now we could apply Avogadro's number to not just individual atoms of elements. If we had something like water, we could say that in 1 mole of water, there would be 6.022 times 10 to the 23. And water is a molecule. So we would use the term molecule there instead of atoms of water. You know, if you had 1 mole of methane, which is CH4, that would be 6.022 times 10 to the 23 molecules of methane. So we could apply Avogadro's number to things that are just like atoms. We could apply Avogadro's number to things that are molecules. And we could use it like a conversion factor, like we talked about on this previous slide. You could say in a mole of water, there would be 6.022 times 10 to the 23 molecules of water. Or you could flip it around and put Avogadro's number up on top if you needed. Over 1 mole of water. So again, Avogadro's number, our conversion factor to go between those two things. Any questions on that there? Okay. So in addition, we also talk about molar mass. And molar mass is a very useful sort of, it's really a conversion factor. And molar mass actually comes from the periodic table. Molar mass is identical. And when we talk about molar mass, it has units of grams per mole. It's identical to the atomic mass that we find on the periodic table. So if we had nitrogen, and that number on the bottom, 14.01, we'll call it. What that means is if I wanted the molar mass of nitrogen, the number that we see on the periodic table would be how many grams there would be, 14.01 grams, in every mole of nitrogen. So the molar mass of nitrogen would be 14.01. If you looked at hydrogen's little symbol up there, 1.008, that means that there are 1.008 grams per mole would be the molar mass of hydrogen. We use molar mass as our conversion factor to go from grams to moles and moles back to grams. And that is a conversion that we do a lot here in chemistry, is that conversion. So what does that really mean when we say it's 1.008 grams per mole? It means that, you know, you have 1.0, if I write it right, 1.008 grams of hydrogen in every 1 mole of hydrogen. And you can use this as a conversion factor as well. So you could say that there are 1.008 grams per mole of hydrogen, or you could flip it around and go a mole of hydrogen up on top is 1.008 grams on the bottom. So we could use it as a conversion factor as well. And pretty much if we start with grams, we're going to divide by the molar mass. That way the grams cancel and we end up with moles. If we are starting with moles, we would multiply by the molar mass, grams on top, moles on the bottom. Moles would cancel, ends up with grams here. So that is the conversion factor as well. In addition, molar mass can also be used for things that are not just elements as well. We could do things like water, for example, and find the molar mass. If I want to know what the molar mass of water is, what do? I pretty much add up all the parts. So I would go to the periodic table. I would find oxygen, which is a part. It will say 16. That means that the molar mass of water would be 2 times the mass that we see on the periodic table for hydrogen. Plus, since there's 1 oxygen here, 1 times the 16 grams per mole that we see for our oxygen, which means the molar mass of water is 18.02 grams per mole. Again, we could use that as 18.02 grams per mole, or if you needed it as a conversion factor the opposite way, you could use it in this fashion as well. You could also do it for that CH4 that we talked about earlier. Again, we would go to the periodic table and we would find carbon. We would look under carbon, it will weigh 12.01. We would add up all the parts here. So we have one carbon at 12.01 grams per mole. We have 4 hydrogens, each at 1.008 grams per mole. And if we add all that together, looking like 1604, I think 1603, 12.01 plus 4 times 1.008, 1604 grams per mole would be the molar mass of CH4. And if you needed to use it as a conversion factor, just like we did above, you could go 16.04 grams per mole, or you could flip the moles up on top and 16.04 grams on the bottom. Question on that there. Now, how many digits do we typically take off the periodic table when we're converting into molar mass? It is actually 4. So this is typically what we do. So depending on your periodic table, you may have more numbers, you may have less numbers, but typically when we pull those numbers off of the periodic table, kind of 4 significant figures is typically what we use to calculate the molar mass from the periodic table. Any questions on that there? Okay. Now, if we kind of tie together the two things that we just talked about, which was Avogadro's number and molar mass, if I had 1 mole of hydrogen, that would have 6.022 times 10 to the 23 atoms of hydrogen. And that 1 mole of hydrogen would also have 1.008 grams of hydrogen. So there is a relationship here of these guys. And 6.022 times 10 to 23 atoms of hydrogen, which is 1 mole, that would have a mass of 1.008. You could also do that with the molecules that we talked about. 1 mole of water would have our 6.022 times 10 to the 23 molecules of water, while 1 mole of water, as we calculated there on the previous page, would have 18.02 grams of water in this particular case. So that is sort of the relationship that we see. I talked about earlier the grams to moles, moles to grams, but just to work it out for you, again, if you had moles and you wanted atoms or molecules, you would go a mole and use Avogadro's number up on top. Moles would cancel and you would end up with atoms. And vice versa here, if you started with atoms or molecules or whatever it may be, you would use Avogadro's number there on the bottom, basically divide by it, and moles up on top. Atoms would cancel, would leave you with moles in this particular case. So that's sort of how you would set up the sort of conversion there to do. Any questions on that there? Okay. Now, as I mentioned before, these are sort of how we do these conversions, and you want to make sure that, you do the proper conversions and not sort of do things that you shouldn't do, and make sure that you don't use Avogadro's number too much, but use it in the proper sort of place. So why don't we look at some examples here and see what you come up with. Why don't you try these two? Why don't you also do this one? How many, let's do grams are there in 25.5 moles of C2H4. And let's do how many moles are there? And let's do 128 grams of C2H4O2. So take a few minutes here and work through all 4 of these here and see what you come up with. And we'll come up hopefully together with the same answers. In case you're not sure, I'll give you the pictures of the periodic table in case you don't have it. Helium, underneath it, 4.003. Add 3 there. We then have carbon, which we saw earlier, 12.01. We also have hydrogen that we saw earlier, 1.008. We have zinc here, and zinc is 6539. And hydrogen and oxygen might be what we need there as well. Oxygen is 16. All right, take a few minutes here and work through each of those. Think about what you should be using, what you shouldn't be using, and then we'll go over and make sure everybody hopefully again is on the same page. See how to approach these guys as well. So first off, we want to know how many moles are there of helium in 5.46 grams of helium. The first thing we want to think of is, should I use Avogadro's number here? And hopefully the answer that you came to is no. There's no mention of atoms. There's no mention of molecules or anything like that. There's really grams and moles. So remember that the conversion to grams to moles are backwards. That is the molar mass that we use to do that from the periodic table, or grams per mole. So we need to go find helium right there at the top. That's convenient. So it says 4.003 scribbled there. That means that there are 4.003 grams per mole for helium. We are going to use that as a conversion factor. So we will start with our 5.46 grams of helium. Just like we did with dimensional analysis, helium's up on top, the grams of helium, which means we actually want to put the number with the grams on the bottom and a mole of helium up there on top. That means the grams cancel, and we end up with 5.46 divided by 4.003, about 1.36 moles of helium here. And in terms of significant figures, we wouldn't look at the molar mass, so we would look at this number, 3 sig figs and 3 sig figs here. Any questions on that calculation there? Now we want to look at the next one. Again, we see we're looking for grams, we're looking for moles, nothing about atoms, molecules. So again, we're going to go with our molar mass approach. In this case, though, we got a few things to figure out the molar mass. So for C2H4, there are 2 carbons. Again, going to the periodic table, we see carbon is 12.01 grams per mole. We would then add that to our other guy, which is 4 hydrogens. So 4 times hydrogen's molar mass, which is 1.008 grams per mole. And if we do all that, we end up with 28.05 grams per mole here, 28.05 grams per mole. And that would be the molar mass of our C2H4. This is not the answer to the problem. This is us really getting our conversion factor to actually use to solve the problem. So now that we have our conversion factor, we'll start with our 25.5 moles of C2H4. Doing dimensional analysis means that moles need to go on the bottom and 28.05 grams need to go up on top. And that would be about 715 grams of C2H4. Any questions on that one there? Looking at the next one, we see zinc and we see grams, we see moles, but again, no molecules or atoms. So again, molar mass is what we're going to use. In this case, it's just zinc by itself. So it will be that number there, the 65.39 grams per mole. Starting with our 0.256 moles of zinc. In this case, we want to get rid of the moles. So the moles need to go on the bottom, which is 65.39 grams. Moles will cancel. This gets us about 16.7 grams of zinc in this case. Any questions on that one there?
Yeah, I have a question.
Yeah.
For the word problems that are in bold,
Yeah.
I noticed on the first problem you canceled out grams, but on this problem you cancel out moles. How will you indicate between the two?
So in this second question here, it was asking how many grams we would have.
Okay.
And the starting number that we had was in moles. So that's how we know we kind of need to get rid of the moles. Is pretty much, it's really it's just a conversion, even though it's kind of known as molar mass and grams per moles. It's really just a conversion of units. So usually in this type of situation, if you're doing like molar mass, whatever the unit you're starting with is kind of the one you want to get rid of. And that's why we did sort of
Okay.
here. And the same thing up here. We're really given the number with grams here, and we were looking all here for moles. So that's again why we got rid of the grams on the first one, and we ended with moles. So that's ultimately what we were looking for.
Okay, thank you. I just wanted to make sure.
No problem. You're welcome. Other questions? Okay, then let's take a look at the last one there, which is, again, we have grams, which is what we're starting with. We want to get it to moles here at the end. So we do need that molar mass. So we got a bigger thing we need to figure out the molar mass of here. So that's C2H4O2. Again, we're just going to pretty much add up all the parts for the periodic table. So we have 2 times 12.01, which is what you find for our carbon. Plus there's 4 hydrogens, which again, if we went to hydrogen, is 1.008. And there are 2 oxygens, which are 16 in this case. And again, this calculation here is actually just getting us a conversion factor to use to actually solve the problem that we're really looking for. And if I did it right there, that is definitely not right. Let's try that again. 20.052 plus a 32. Try that. 60.05, I think, is much better on that. 60.05 grams per mole. So again, we're going to start with the number that was given to us, and that's 128, and the units there are grams. So that is how we're going to know we want to get rid of grams. Also going to tell us that we need to put the gram part of this on the bottom, which basically means we're dividing by it. Grams will cancel, will leave us with moles. And if we do that, we will end up with, looks like something like 2.13. And the units would be moles of C2H4O2. Any questions on any of those there? This is definitely a conversion that you do a lot in chemistry, and a lot of the times you're going from grams to moles. So that's a very, very, very common conversion that you do need to be able to do. Any questions on any of those there? So let's take a look at 2 last ones here. Why don't you figure out what is the mass in grams of 1 gold atom? And I'll give you gold here. Maybe I'll give you gold if I can see it. 197, I believe it is. We'll go with that. 197.0. And while we're at it, let's say if we had 32 moles of water, How many molecules would that be of water? All right, so take a couple minutes here and see what you come up with, and then we'll talk about it. Atom means that I do need to use Avogadro's number at some point. And remember, Avogadro's number is our conversion between atoms to moles, which is good because I ultimately want grams. And I know to go from moles to grams, that's my molar mass. So we're going to kind of use all those things together. So we would start with one gold atom. And remember that in 1 mole of gold, there would be Avogadro's numbers worth of atoms. And again, we're going to use that as our conversion factor. So we want to get rid of atoms. So we would actually put Avogadro's number on the bottom per mole of gold. If I stop the calculation right at this point, I am in units of moles, which is close to what I want, but I actually want grams. So that's going to require the molar mass, which we would get from the periodic table here. And again, that means that the molar mass is 197.0 grams per mole for gold. And I'm just going to continue on with the calculation. I got moles up on top, which means moles need to go on the bottom, and 197 grams of gold goes up on top. Moles will cancel, and I am left with just the units of grams, which is good. We're basically taking 1 times 1 times 197. We're dividing by Avogadro's number. Make sure, again, you use your exponent button. And it ends up with something like 3.271 times 10 to the minus 22 grams of gold. And that is a super small number, which does make sense since we're talking about one individual gold atom. It would be a super, super small mass. I went to 4 significant figures because this is kind of like an exact number. So you could kind of go to as many numbers as you want. So I took it to 4 because the molar mass was in 4. Question on that calculation there. All right, we will wrap it up there here for today. Since we're a little bit over, sorry about that. Obviously, next week is no exam, but we are going to have a quiz on Wednesday on nomenclature. So I believe that was part of this stuff. So we're just going to do a quiz on nomenclature. So that's naming, that's formulas, that's polyatomic ions and stuff like that. We'll do it at the end of lecture on Wednesday. The exam obviously has been moved now until after spring break, which is the following week, and we'll do it after spring break. So by next week, we'll know exactly sort of where we're at in terms of which day it will be, Monday or Wednesday, but it will be after spring break. Any questions on that?